Hey, nice to meet you. Thank you, Professor Lilo Rivero, the Institute and the University for hosting us. So my name is Mateus. I'm a software engineer at the Oasis Protocol Foundation. And today tonight we're gonna have the workshop on Oasis Sapphire, a confidential blockchain. Thank you, Professor Lilo Rivero. Yeah, so looking at the Institute and
I won't take up your time. I'm Mika, I'm the head of community for Oasis. If the students want to join us afterwards on our Discord or our Telegram, they can find all of our links on oasis.net. That's our main website. I'm just here to offer support. I'll let Matiush do his thing.
Hello, everybody. My name is Mateus. I'm from Belo Horizonte, and I'm an ambassador at Oasis Protocol. I've been talking to Ilo in this past few weeks in order to organize this workshop for you. It's been tailored specifically for you. I think you will enjoy it a lot. I hope you enjoy it. Today we're going to cover some topics such as an introduction to blockchain, to Oasis Protocol, to smart contracts. We're going to have a hands-on experience deploying a smart contract in the Sapphire network. And yeah, I hope you will enjoy it. I think you can go on, perhaps, Matej.
Okay, let's get started. Right, so this will be a 2-hour workshop, but I think we can make it slightly shorter, and then students may have time to hack, and maybe I can offer them one-on-one support if they run into any issues. So what are we going to learn? First, we're going to look at the Oasis architecture. So as I mentioned, the Oasis network aims to be a confidential, private blockchain. So there are quite some concepts here we need to grasp. And then I designed this workshop in kind of a three tasks. The first one will be we will build a simple smart contract running on Oasis Sapphire, and we will just use Remix. This is the browser IDE, so you don't need any special development environment, any special tools installed. You can just hack inside your browser and get your smart contract deployed. The second task is slightly more demanding. You will need to have the Node.js installed locally, and by this we will have this special Sapphire wrapper that encrypts the transactions. So for task 1, there will be no encrypted transaction, just encrypted storage. For task 2, we will also have this end-to-end encrypted smart contract transactions. And the task 3 is also tailored towards the front end and towards the authenticated calls. So it's not only transactions, you can also have queries for Ethereum-ish like smart contracts, which don't require any gas. And Oasis Sapphire is slightly more specific about this because, well, it's a confidential blockchain, and the queries cannot be just public because the blockchain is not transparent, it's encrypted. So all the calls need to be signed, need to be authenticatable. So we're going to look at how do we do this on Oasis Sapphire. And then the last section is about like, okay, this is now the workshop. What can you do with it? Like what to do next? I will cover some interesting projects the Oasis team built, and also the hackathoners around the world built in the past few years. So I hope I'll motivate you to start building on Oasis and join our community. And yeah, this is it. So I suggest we go on. The prerequisites, as I mentioned, so I hope you have some basic programming knowledge. It's not necessarily Solidity. So Solidity is this de facto programming language used to write smart contracts. Some knowledge on Python or JavaScript is sufficient, just that you can follow, the flow. Also, we will be using command line interface. I will be running Linux, but the commands are basically the same on other operating systems when it comes to Node.js. And yes, as I mentioned, the Node.js environment should be installed locally for task 2 and 3. And PNPM is another package manager, which you just simply install using the npm command. So PNPM is a special package manager on top of the npm, which comes shipped with the Node.js. Okay, so let's talk about the Oasis architecture. So meet Alice and Bob, a friendly couple back in the 90s. So what happened in the 90s? You had this PC era, which started all around the globe. And what was specific in that era is that you had the computer, and all the computation was done inside the computer, basically. The only input and outputs are, well, the keyboard, the mouse, the screen, maybe some floppy disks, later CD-ROMs. But the bottom line is there was no internet yet, at least not, widely spread. So we didn't have some other architectures common in that era, but for the ordinary Alice and Bob, this was the main interface and the main how things were computed and done. So everything is inside that box. No data leak is possible otherwise than someone actually stealing your computer. Okay, so if we draw the arrows, the diagram would look like this, right? Right, and then comes the internet. And things start to get really interesting. So now the computer is running something called the web browser. So the architecture is like this. We have the Alice and Bob using the web browser to access the internets, and the servers on the other side actually do the computation. So when it comes to input and outputs, this web browser is just a kind of a terminal that makes sure that the data is delivered to the server, and then the server stores the data, processes the data, does all the computation. And basically this client-server architecture is what is today known as the Web 2 era, and the architecture didn't change much in this regard. Okay, and the upside of this approach is that you can have multiple clients accessing the same application from wherever on the world, and they can just use apps, and everything is beautiful, right? Except that there is this blonde guy which has a trustworthy face though, but he's the administrator of the server, right? And basically what this means is that he has access to all the data stored on the server and processed on the server. So this is not, this is a very strong assumption if you consider risks, right? If you have sensitive data, this is something that's really important, and data should be cared very carefully. It's when it comes to trust. Okay, and then comes the blockchain and the distributed ledger. So in the Bitcoin, so the Bitcoin white paper was published in late 2008, and it laid the foundation of the so-called distributed ledger. So here you have a concept of the distributed network. So distributed networks were already before the blockchain era, of course. But what Bitcoin was focused on is how can we make use of the distributed network for building a money, a peer-to-peer electronic money without the central authority. And that's why the Bitcoin used this decentralized architecture. And what this means is that if you want to communicate with other nodes, you also need to run your own node. And there is no client-server architecture. Everybody is both the client and the server at the same time. So this is very, very robust, because if you take one node down, the network will still function. And previously we had this, if you remember, the so-called HTTP requests. Here, the communication between the nodes is dependent on the protocol, but it's not HTTP. It can be whichever protocol the nodes speak. And all the computation is done on each node, because nodes do not trust any other node. So they don't trust, they verify. Which means that every node needs to know everything, and every node needs to compute everything. And this is the only way the node can be sure that the other node, is not lying. So this is also something called the Nakamoto consensus, which we'll talk about later. And when sufficient number of nodes reach the consensus, then some transactions or blocks of transactions can actually be verified in that regard. Okay, but in practice, so I just added one small here in between another node. In Ethereum world, we have something called the Web3 gateway. So in practice, what the original Bitcoin architecture was about is that it may not be that practical when it comes to applications. So if you want to have some, I don't know, game, like betting game running on chain, or some DeFi application, doing trades, you should have some nice application, like a web interface for that application. And then when it comes to users and their phones, for example, they cannot run their full node inside the phone. They usually have something lighter, for example, a web browser. And it's a common practice in Ethereum, at least, that we have something called the Web3 gateway. So basically, on the left side here, you have the Web2 world with web browsers and this client-server architecture mind. And on the right side, you have this Web3 distributed world, distributed network. And then in between, you have this Web3 gateway, which which translates the HTTP requests into the peer-to-peer transactions. And why I'm telling you this is because this Web3 gateway is a single point of failure. So if you are using a web browser to access the nodes, basically if the Web3 gateway goes down, you either need to find another Web3 gateway or you will not be able to access the blockchain. Compared to the the Bitcoin architecture, where it's the full node and like you connect to a set of peers, and basically you can rest assured that your connections are well covered. If one node goes down, you still have access to the rest of the nodes at the same time. Okay, now let's talk about the Ethereum virtual machine. So the Ethereum virtual machine is something that executes transactions. So back in the Bitcoin world, back in the Bitcoin time in 2008, 2009, the only kind of transactions were send tokens to, not to some address, but I will make the condition that whoever has a secret key that is able to decode my output is allowed to spend the Bitcoins on the other side. And most of this, it's called the script language, is very primitive. So the primitives are like comparisons, verify the signature, Schnorr signature, sign, these basic cryptographic operations. And it is not Turing complete language. Basically, you do not have for loops, for example. You have some kind of the if conditions there, but that's about it. So what the Ethereum idea was behind, like, can we expand Bitcoin to run a more generic programming language, something like JavaScript, for example? And at that time, the community, the Bitcoin community, claimed that it's a far too big risk to support full Turing complete language inside the blockchain interpreter. And that's why, the Vitalik idea was to found their own foundation called the Ethereum Foundation, and he built a completely new blockchain, basically. And at its core, it's running this Ethereum virtual machine that executes a slightly more complex transaction. So it still supports, the language still supports, the virtual machine still supports sending tokens from one address to another address. Also multiple addresses, so I'm talking about the multisig here. But apart from that, you can also call some function at some smart contract that is deployed on-chain. So the smart contract is basically an application that is executed on all the nodes again, so it's still a distributed network. And the transaction has this call data, which is usually the function inside the smart contract, and parameters you want to call. If so, it's not just about sending tokens. Now you can also call functions of smart contracts. Okay, but how are transactions stored on Ethereum on blockchain? So we have this public ledger. So it's just a list. It's a ledger of all the transactions, like from to the call data, the amount of fee the transaction pays, and other details. How is the contract state stored on Ethereum chain? So as I mentioned, the smart contract is in fact an application running on chain on each of those nodes, and the behavior of the smart contract needs to be deterministic, because all the nodes execute everything. Then the result of the function always needs to be deterministic in order for nodes to verify that the transaction is really that the result of the transaction is really the one that's claiming to be, so they can verify the transaction and say that, okay, this transaction is valid, this block can be verified and put into the link of blocks called the blockchain. So the smart contract has a notion of this smart contract state. This is basically the variables stored inside your smart contract application on chain. So if you have some, I don't know, integer, my number is 10, you store this number 10 somewhere, and this somewhere is called the smart contract state, and it's basically the key value store of each smart contract that resides on each Ethereum node. And this contract state is public, right? So everyone can see any field, any variable of any smart contract. It's no encryption, so you can basically just extract raw value of the variables of any smart contract you want. There's even a special call. It's called the ETH get storage at. So this is the the core Ethereum function built in the protocol that gives you the value of a specific cell inside the smart contract, right? So you basically say what is the address of the smart contract you want to access, what is the address of the cell you want to obtain, and it just gives you back the raw value. So then it's up to you. I mean, if you know that this is an integer, then you will interpret it as an integer, and then you can do something with it. If it's a string, if you know that it's strings. So basically, it's a kind of a memory dump, but using the blockchain for memory. Okay, but the problem is that if you go to the real world cases, you may find out that like most of the applications have this public part, which can be publicly accessible by anyone, and you have this private part, which should be just known to maybe to the authors of the application, or to the ones running the server, or maybe even to nobody. Just that it's just there, it does its job, and no one actually should be able to see inside the primitives, like what's going on inside. And this is something similar to like if you want to send a letter. There's this envelope, and there's a public address there. You stick a stamp, but inside the envelope there is a message or some content which no one should see apart from the receiver, right? So you have this public part, and you have this secret part that should not be viewed by anyone else than the receiver. Okay, and Ethereum doesn't address this, obviously, because well, it's fully transparent. There is no privacy. So the research questions we had was like, can we make a confidential blockchain? Can we encrypt the world state trie so that the contract state is encrypted? Like, okay, let's encrypt it. But now the problem is that, like, if it's encrypted, how will nodes verify our transactions? Because nodes need to execute the transactions. The transactions require access to smart contract state, and like if you have the smart contract state encrypted, you need to decrypt it in order to run the transaction. But now, if you want to decrypt it, like where will you put the key? Because it needs to be accessible, right? And now that's tricky, because the only space the smart contract can access is the smart contract storage. Like the smart contracts don't have access to external servers, HTTPS or whatever. So it's a very closed world for the smart contract when it comes to scope. So where to put the key? And in fact, it smells that it's theoretically impossible to solve this problem by using sole cryptographic primitives. So we were exploring further, and we came up with an idea to use novel technology called the trusted execution environment. Okay, so here comes the Sapphire. It's a fully confidential EVM, and what it is, so it's our production-ready confidential EVM blockchain. It's running on the Oasis Network, and we are using this technology called the Trusted Execution Environment, or TEE. So this is the problem of storing the key I mentioned earlier. Well, this is the hack we're using, how to store the key and perform the computation in a confidential manner. So the smart contract storage is encrypted by using this approach, and also the transactions and contract calls, the queries, can be encrypted. So this is the preferred way. Everyone should be using it. But to maintain the backward compatibility with Ethereum transactions, transactions can just be, the original Ethereum formatted like. So we don't break backward compatibility if you already have an application and you just want to run the existing Ethereum app on Oasis Sapphire. Right. Okay, so maybe just a few words about the TEE. So there's a very, very nice description on Wikipedia. I will just borrow it from there. So TEE is a secure area of a main processor. It helps the code and data loaded inside it to be protected with respect to confidentiality and integrity. Okay. So data confidentiality prevents unauthorized entities from outside the TEE from reading the data, while code integrity prevents code in the TEE from being replaced or modified by unauthorized entities, which may also be the computer owner itself as in certain DRM schemes described in the Intel SGX. Right. Oh, so I'd point out here two terms. So the TEE does both. It does confidentiality and integrity. So the idea is that, do you remember the blonde, trustworthy face guy with glasses at the beginning of the slides? Well, that's the server admin. And what TEE enables is that you don't need to trust the server administrator, because your application is running inside this enclave, which encrypts the main memory, like physically encrypts the main memory. And only inside the CPU, you have these tamper-proof registers where you store the decryption key. And the communication, the memory blocks physically between the CPU and the main memory is encrypted. So even if someone, it's a physical oscilloscope and try to monitor the signals, they will just get the encrypted data. Or if someone is running your application inside a virtual machine, hypervisor-ish, whatever, that virtual machine requires this trusted enclave to be spun up, or otherwise it will not want to start. And if that succeeds, then even if he dumps the virtual machine memory, he will just get, again, encrypted memory. He will not be able to extract anything that's going on inside this trusted enclave. And another term here is the integrity. This means that, like, how good is a confidential program if someone can, modify it, and then that program can leak data, right? So you also need to assure that the program running inside the TEE has this integrity proof. So it hasn't been modified once it was loaded inside the memory. Right, so now you can get the idea. Like, so we have this TEE, and what we do basically is we took the Ethereum virtual machine and we ported it over. We rewritten it to be executed inside the this TEE. And so yeah, TEE is not like obvious. So the only company currently that is compatible with our stack is Intel. So Intel has this 5th and 6th generation of Xeon CPUs that support. So the commercial name for the trusted execution environment is Intel SGX. That stands for the safeguard extension. And then there's a newer generation of the TEE. It's called TDX. It's a trusted domain abbreviation. So these are the only two, currently on market, to our knowledge, technologies that effectively use this TEE, and that you are able to run, the whole operating systems, if you want, inside the trusted enclave. We'll talk about this a bit later, but when it comes to Sapphire, so Sapphire currently requires Intel SGX. So if you want to run your Sapphire locally on your node, you must have Intel SGX. Okay. Okay. So how does Sapphire smart contracts run in practice? So each contract state is encrypted using a different key. So when there's a transaction that needs to be executed inside the confidential contract, the first thing that happens is the EVM, the execution engine, for the transaction, requests from the key manager a key to decrypt its contract state. And there's a certain protocol here that, so the key manager needs to verify that the Sapphire requests was really originated from the trusted enclave. And then the key is obtained, the smart contract state is decrypted, and then the transaction is executed. And the new input and output, so the IO3, the new contract state, is written back to the key value store. So since we're at the technical event, the data structure we are using to store data is called the Merkleized key value store. It's basically, in our case, it's a binary tree. It's actually a trie. So the path from the root to the leaf can be arbitrarily long. And this Merkleized term means that every node contains the hash, and the leaves contain the hash of their data, and then all their ancestors contain the hash of their children. And at the end of the day, you have this root node, and that root contains the so-called root hash. And why is this data structure so usable? It's because if you change a single bit inside any of the nodes, basically the root hash will also change, because once you change the bit, the hash of that node will also change, and then this will, cause this domino effect on the leaf to root path, and basically change the hash of all the nodes on that path, and eventually it will change the root hash. So usually this is also a case for Bitcoin example. When you want to prove that the block is really valid, you just need to store the root hash, because any bit you change afterwards will affect the root hash, and that's the only proof you actually need. Okay, so keep in mind here that even though the contract state is fully encrypted, the node operator can still see like which memory locations did you access while executing the smart contract. So it cannot see which data did you read, because data are encrypted, but it can see, the node operator can see which memory locations did your smart contract access. So this is a so-called access pattern, memory access pattern attack is still possible. Right, so by using the TEE, we can achieve some really interesting features. We can finally have private computation, like you can have the smart contract that has some certain business logic inside, and it has this business logic, for example, trading logic that can be hidden from the outer world. You don't have this transparency anymore. Then you can do randomness. You can have this, online slot machines that you cannot say upfront, like which number will be the next one, which is not trivial, in the distributed networks, because everything needs to be proven. It's really difficult to implement this random beacon on chain, because the nodes still need to prove that the random number was really generated in a random fashion, and it's not a trivial task to do this in a distributed environment. So there are many issues. Many projects were tackling this issue, and it's not trivial. Right, then you have private storage. So you can store sensitive data, GDPR, private keys, whatever. So this is another very useful feature. And you have this end-to-end encryption, meaning that all the transactions, not just the contract state, also the transactions are encrypted and stored on the ledger. So the ledger is still public, just the call data of the transaction is encrypted. Optionally encrypted, but it can be encrypted, and we suggest to use encryption like always. It's similar to the voice and chat applications. So people are just not using the end-to-end encryption, even though they could be using. And then, the big companies started to turn on the end-to-end encryption by default. But then come the governments that want to prevent using end-to-end encryption by law, and so on and so forth. So it's a similar story here. Okay, now back to our diagram. So we have our Alice and Bob here, which are slightly older now. They have the web browser, and now they want to access the confidential blockchain. So we still have this Web3 gateway here, because Alice and Bob are using their Web2 browser. And now they are this Web3 gateway is transcoding the HTTP requests to encrypted peer-to-peer transactions. And the computation is now done completely inside the trusted execution enclave, right? We have this padlock. Wherever you see the padlock in our documentation or tutorials, that means that, yeah, it's this trusted execution environment is being involved. So what this gives you is the computation is confidential and it's also verifiable, so that you can rest assured that the computation was really legit. And in a nutshell, what our architecture looks like, so it's not just the Sapphire we are running. Our network is slightly broader. So we still have this consensus layer. So the consensus layer is similar to what Bitcoin has. So just simple transactions for sending tokens from one account to another account, and doing the governance. So electing, which node is allowed to sign the blocks, verify the blocks, and then so we have these committees of nodes doing all kinds of stuff. So the governance is done on the consensus layer, and then we have this compute layer, which can run multiple chains. One of them is Sapphire, we will use today. But then you can also build, even yourself, you can build and deploy your own blockchain on the Oasis network for some certain amount of tokens. You can just register it and define which nodes will be running your blockchain. And then, yeah, so this is the architecture. By the way, we also have another blockchain called Cypher. So this one wasn't compatible. The smart contracts you write are in Rust and then compiled to WASM. Sapphire is EVM compatible, so we have the Solidity language or Viper. And then we have our more specific partner blockchain called PontusX. And then there's this Emerald blockchain also, which is EVM compatible, but it's not encrypted. So basically, the bottom line is you can really run a bunch of blockchains, and this is also the way how we tackle this scalability issue when we designed our protocol. Okay, so maybe now I should start with our first task. Maybe are there any questions so far? If not, then I think we can get started. So first, I'd like to ask you to install the wallet. So if you don't have one yet, I suggest you install. Yeah, sorry.
Sorry, Mateusz. I think there's a question by Ana Alice in the chat. Can you read it?
Yeah, I see it, yeah. So the question is, what is the difference between a permissioned blockchain and what the Oasis network does? Basically, so the permissioned blockchain is a term where only a small amount of nodes govern the whole network. At Oasis, there are currently 120 validators running miners in the Bitcoin terms, which decide whether some block will be verified or it will not be verified. And among those 120 nodes, there is exactly 0 nodes run by the Oasis Foundation. Okay, so that's also one of the strategies we have, that our network should not be permissionless, because if it's permissioned, sorry, then the network it doesn't have any sense. Like why do you want to have a permissioned network if you want to do blockchain, right? So in our case, yes, the network is permissionless. So this is I think a big thumbs up for us, and we also put so much effort into communicating with the node operators to run their actual nodes, help them out, setting up all the SGX hardware, configure it, and of course, yes, they earn some fees by verifying the blocks, but it's a lot of effort if you want to actually have the permissionless blockchain. yeah, it's much easier just to have like 5 nodes running the permissioned closed like network of the nodes, and you just say, yeah, my network is blockchain. Yes. Okay, cool. So let's get started. The wallet, right? So let's see. Let me just maybe minimize this. So you should go to MetaMask if you don't have it yet. And then you download the extension for your browser. Or you can just go ahead and download Brave browser, which has the crypto wallet already installed. And then once you install the extension, so I'm using Firefox. You can also use Chrome or some other Chrome-based browsers. So they'll have this manifest extension protocol, so you can just install the MetaMask. And in my case, I already made an account here. It's called Dave. This is the address, and I have 200 test tokens. So initially, when you will set up your MetaMask for the first time, you won't have any tokens here. So let's see. The next step is okay. So before getting test tokens, you will also need to add the Oasis Sapphire testnet Web3 endpoint to your MetaMask. So here in the top left corner, you have a bunch of blockchains, right? So we have the Ethereum, Linea, Base, and so on, Arbitrum, for example. I think by default it's only Ethereum. I also use some other chains. And you need to install, or not install, just add the Oasis Sapphire testnet. This one we will use today to deploy our smart contracts. So to do so, you can either just hit the plus icon here and enter details manually, or it's easier if you just follow the link. So at our documentation website, if you go under Build, Sapphire, and Network Information, you then have this list of RPC nodes. So RPC stands for Remote Procedure Call, and this is the the Web3 gateway I talked previously that transcodes the Web to HTTP requests into the blockchain requests. And here we have this Oasis Protocol Foundation managed node. So we're running both the mainnet and testnet Web3 gateways. So just click on this Add to MetaMask button. And so I already have this endpoint installed. But if you don't have it, then the pop-up will appear and the Sapphire testnet will be added to your MetaMask wallet, like so. And the details are the following. So yeah, you can also see it here. So the chain ID is 23295. The URL is https testnet.sapphire.oasis.io, and the token is called the test token. Right, okay, let's move on. And then to get some tokens, so in order to deploy a smart contract or send transactions on chain for preventing spam, there is certain fee that is always required to send along the transaction. And to pay for the fee, you need tokens. And on the testnet, we have these test tokens. So you can just go ahead to faucet.testnet.oasis.io. Let's see. Okay. And this wonderful Cloudflare verify you are human pop-up. Okay. So here, basically you select the Sapphire chain. So these are the chains I mentioned. So we have this consensus layer, and Emerald and Sapphire and Cypher are currently supported here. So each of those chains have their own, they are all using the test tokens, but you can transfer tokens from one chain to another chain. So you can just click Sapphire here and they will be transferred directly to your account on Sapphire. So just paste the address here. So I will use my account here. Let's copy this one, paste it here. I'm not a robot, I hope so. So, okay, request test tokens, and the tokens are on the way. You will get, I think, 150 tokens. Yeah. And if we now check our balance, in a few moments, I should have like, what, 350 tokens here. Okay. Cool. Let's move on. So the next link I'd like to point out is the one we already used for adding the testnet network. So it's docs.oasis.io. It's a very, very extensive collection of technical docs. But basically, so this use Oasis is a more general documentation on what our architecture looks like, why are we doing what we're doing. Then you have this build section, which is how do you build on Oasis. Currently, it's all about Sapphire, the confidential EVM, and Ruffle, which is something really, really new. So we will be launching that in a few weeks. But basically, we have the public beta access available. You can build, Ruffle stands for runtime off-chain logic, and you can build more compute-intensive off-chain applications, which are still provably doing what they should be doing, but are much more efficient. So it's not all about blockchain anymore, but we kind of made a hybrid system for running some stuff off-chain and the rest of the computation on-chain. So it's a pretty novel technology. You can go ahead and try it out. And then the get involved is more the community-oriented part. Run node section is about if you want to become a node operator and earn some fees for that. And then the develop core are the hardcore Oasis core documentation on primitives and all the data structures used in Oasis core. All right, so let's get down to it. Task number 1. So we will talk about confidential compute and confidential storage, the two very unique features of Sapphire compared to Ethereum. So first, I will touch briefly the precompiles. So the precompiles are built-in functions. And so you have this Solidity language, which is similar to JavaScript. So we have some functions, you have integers and strings and some hashing operations. It's a pretty simple language, but in order to extend the language, to extend the functionality of your smart contract, the Solidity already defines something called precompiles. And basically, it means that at some address, you can call some function that is part of the Ethereum virtual machine. And those are pretty useful. For example, you can do a bunch of cryptographic operations, which would be really, really costly otherwise if you implemented it in Solidity. So we just use these precompiles, which are much, much faster and cheaper. I just have one more question, maybe. So Iago asked me before we move on, maybe I should really take this one. So Iago is asking, how is data verifiable if it's private? So this is a pretty complex question. But it comes to this. So if you go down the rabbit hole, you can always audit our code and see that there are no leaks anywhere built in, that the data stored inside the smart contract can go somewhere externally. Okay, so that's the formal answer, like how can you rest assured? And if you then go from the transaction running inside the TEE all the way up, you know, to the whole Sapphire EVM running inside the TEE, and then all the way up to the Web3 gateway transmitting the transaction or returning the data, all the way up to the client software running in your browser, then you will basically see that once you have this end-to-end channel set up, you can rest assured that the transaction will be decrypted only inside the smart contract, inside the this execution engine, and that execution engine will not run otherwise than inside the TE, inside the trusted execution environment. So that's how you can rest assured that it's running. Yeah, it's not leaking anywhere. I may add here that our trust assumption is that we trust Intel, right? So if Intel integrates backdoor into their CPUs, then the whole model is broken. I mean, you need to trust your chip manufacturer, but I mean that's the trust assumption you take, right? Because you will always run your software on some hardware, and like any hardware manufacturer can build in backdoor, and there's nothing you can do about it, right? So our trust assumption is that yes, we trust Intel, and Intel implemented this attestation mechanism when you spin up your trusted enclave. There's a certain attestation mechanism that rest assured that makes sure that the software running inside the enclave is really tamper-proof. So in our case, this is the Sapphire EVM we are running inside the TE, and for this, yes, we rely on Intel that this attestation is legit. Okay, so this is the long version of the answer. Yeah, I hope it makes it clear. Otherwise, you know, just ping me and we can discuss it. Okay. So what do precompiles have to do with Sapphire? So apart from the original Ethereum precompiles, we also support our own precompiles because we have this confidential EVM, and we can do a bunch of more interesting stuff. For example, we can generate random numbers inside the Solidity smart contract, which cannot be done if you're running the non-confidential, transparent blockchain. We also can, because you have the random number generator, you can also generate a private key, and you can also derive then the public key, and you suddenly have this whole, asymmetric cryptography available on chain. You can also encrypt and decrypt data on chain. You can sign transactions on chain. You can even sign Ethereum or Bitcoin transactions, everything on chain. And why do you want to do it on chain? Well, because you can trust the on-chain computation. Every node is running the same instance, and that's the whole idea of blockchain. You don't trust, you verify. So if you have your computation running on chain, it cannot get any better than this. And now you can actually, provably generate and sign Bitcoin and Ethereum transactions if you're using Sapphire. There are also some precompiles for gas padding. Why? Because transactions still show how much gas did you spend when executing the transaction. So that may reveal maybe some confidential data of your smart contract. And as a good, Solidity developer, you want to make sure that every smart contract function spends the same amount of gas, regardless of which border cases are going, which branches are, if statements are taking different flows. So this way, you can cover maybe the internal state of the smart contract. So if you have the if statement, if balance is greater than 0, then you can do a bunch of computation. If balance equals 0, then you just skip something. So this is something you should never ever do in a confidential smart contract, because this way someone will see that. So if you spend more gas, then the balance is greater than 0, right? So how does gas padding save you? Well, basically you say that at this point in time, I will always spend X amount of gas, regardless of whether balance is greater than 0 or lesser than 0. So this after if statement, we just put this gas padding precompile and spend like maybe 10,000 gas. And regardless of the flow, then it will always spend 10,000 gas, right? Okay, so basically, if you want to learn more about smart contracts, the full reference guide is here at api.docs.oasis.io. But next, let's get our hands dirty and let's build a simple random number generator game. So what we will be using is this random bytes function, random bytes precompile. And so previously, how do you import this Sapphire precompiles? There's a special NPM package called Oasis Protocol Sapphire Contracts, and inside the Solidity, you just import it like so. And then once you have this Sapphire sol imported, you can call something like Sapphire.randomBytes and the number of random bytes you need and some nonce. And here, basically, this one will return you 32 random bytes. And this is much faster than the verifiable random functions. This is another concept other projects are trying to implement for random number on-chain generation. Okay, and let's get down to it. So let's open Remix. So let's go to remix.ethereum.org. So we are trying to be as compatible as possible with Sapphire. So Sapphire tries to be as compatible with Ethereum as much as possible to use, all the wonderful tooling that the Ethereum community built over time. So we don't, discover the wheel all over again. Okay, so the first thing you will notice is this default landing page, and I think I will just make a new. Let's just make a blank workspace. Let's call it Puki Minas guess number. Okay, and let's add a new Solidity file. I will call it guess number.sol. And this is the space for our Solidity code here. I will just get back to my slides and copy over this snippet. And we will revise it then. Yes, I am pasting code and I am selling my left kidney for it. Yes, okay. Cool. So if we go through the code, what I did here was I imported the Sapphire.sol contract. I'm not sure if hopefully this will work, and also download the package. So keep in mind the Solidity language version we currently support in Sapphire is 0824. I think the latest version is 0830. We're not there yet, so there are some EIPs adding some opcodes, very low-level opcodes of the language, which we currently don't support yet. But we are slowly catching up the Ethereum virtual machine. So hopefully, if you just put down the 24 version, that is sufficient for you. It most probably is, but just keep in mind, if you forget this Pragma version here, it may be compiled with the 0830 or some newer versions, and that won't be deployable on Sapphire. Okay, now the smart contract looks like this. So we have this guess number smart contract. There will be some 256 bits long number. This number will be private. So this is similar to other programming languages. So we have this field here, this member, which is private, and it will not be accessible from external world using that ETH get storage at call, because the smart contract state, as I mentioned, is encrypted. Okay, and inside the constructor, what do? it's a very neat call here. So basically, we just generate one random byte. And then, so this random bytes gives you the array of bytes. So I just take the first one. And then I will use this modulo operation. So among 0 and 255, I will just pick the random number from 0 to 9. Okay, and this is during the constructor phase, right? So the number is now between 0 and 9. And then I will have this guess function here. So the user will try to guess what was my number. You know, what was the random number that got generated during the smart contract deployment. And then if the number is smaller, something like too small will be reverted. If it's too big, the too big message will be returned, and otherwise it just return true if you guessed the right number. So a very simple smart contract, but really, you know, showcases the unique feature of Sapphire that you can just, you know, generate random numbers on chain. Okay, now let's see if this works. So let's compile it. Hopefully, okay. I need the dependency. Yes. Oh, the compiler. Yes, I need the compiler version 824. Okay. So the compilation now succeeded. Awesome. And now let's deploy our first smart contract. So this is the compiler tab here we use. Now let's move on to deploy tab. Here we will use our injected provider, the MetaMask. So this IDE, the Remix, also has some built-in support for deploying smart contracts directly to Ethereum, you know, mainnet, testnet blockchains, or you can just use the injected provider. In our case, MetaMask. It will connect to your MetaMask extension and just get information from the extension, like what is the network you want to deploy to, the account that will be used for deployment, and so on. Okay, so now this was already detected. So the chain ID 23295 will be taken. So this is the Sapphire testnet, and this is my account. And now I think if I just click the deploy button, okay, so the MetaMask pop-up now asks me to sign the transaction, and this is the contract deployment transaction. Okay, so let's see. Okay, so the transaction seems to be going on. It was submitted. Okay, it is pending, and now it's confirmed. Awesome. So the block time in Sapphire is 6 seconds compared to Ethereum-ish 12 seconds. So it's slightly faster. Also, let's check out the transaction on our wonderful Explorer. So if you click on the View on Block Explorer, so this is the explorer.oasis.io. This is our in-house Explorer. It's also open source, and it can also index whichever EVM-compatible blockchain you want. But currently, it's just used, you know, by the Oasis Foundation to index Sapphire, and it also has this extra confidentiality support for indexing, like if the transaction is encrypted or it's plain, and so on. So the contract deployment, contract creation transaction we just did is plain. It's not encrypted, which is also the right thing to do, because usually you want people to see, you know, the bytecode, the business logic of your smart contract, so that they can verify it and audit it, that it's, you know, legit and doing what it's supposed to do. Yes, and the raw data, the amount of fee we paid, so 0.02 test tokens. Okay, so our contract is now deployed, and now during the deployment, this random number was generated and stored inside the smart contract state, and now we can you know, run this guess query and try to guess the number. And I say that the number is, let's say, 5. So just go ahead and press this blue button here in Remix, and it will initiate the query. And no, it says it's too big. So is it number 3? It's still too big. It's number 2. It's also number 2. Yes. So that call succeeded, and it returned true, right? So this is a very simple, game. Like let's play what is the right number, and then you can imagine that you can implement like whichever casino game, gambling, whatever, with this random number generator concept. Okay, now before moving on, can we extend? So maybe this is the task. So we deployed the contract. We checked the transaction on chain. Yes, on our Explorer. Now the question for enthusiastic students out there, like, would you know how to? So currently, the random number is just generated like once you deploy the smart contract, and it stays the same all the time. Like for any Ethereum developers out there, would you know how to implement the random number generator so that it generates a new random number each block, for example? Because the problem with the blockchain is that you cannot store some event mechanism inside the smart contract and say that once every block is generated, call some, generate me a new random number function, for example. So the smart contract is just staying there. It's living inside the inside the blockchain, and the only way to change the smart contract state is by calling the smart contract. So by transmitting transaction on chain, and then transaction only can change the contract state. And for signing the transaction and submitting the transaction, you always need some client, some person on the other side to initiate that transaction, right? So my question is like, how can we make this guess number game more intriguing and try to generate a new random number on each block, maybe, and still using just read-only calls, so without paying fees and without changing the blockchain. Well, the problem if you run it locally is like then you can cheat, right? So it must be run on chain, yeah. Okay, so I'll give you a hint. So the Solidity language has this. Okay, now I will show you the solution already. Okay, one. So the Solidity language has this field called block.number. So this block.number gives you the current, height of the block of the blockchain. Now, what you can do is inside the constructor, you don't generate the final number. Okay, you just generate a very big seed. So in our case, let's use the 32 bytes random function here, and then inside the guess function, we do something like this. We take this seed, this underscore num, and we concatenate the current block number, right? And then we hash those two. And so hashing is built in the Solidity language. It's the function called catsac256. So this snippet here will basically gives us a unique hash each time the block number changes. So what remains to be done is you just need to use the modulo operation on the hash to be inside the 0 to 9 range. And by doing so, you can then have a new random, in quotes, number every block, but because it's not random, it's just, you take the seed, which is generated once, but because no one knows the seed, you can always combine the seed with the current block number, and you'll get, the unique new random number for the user, from the user's point of view. And yeah, you could hack this like so, for example. So maybe let's try if this works. Let's compile it. And use local variable. Expected num. Yeah, so expected num. This should be better. Okay, and let's deploy it again. So this is the old instance of the transaction. So once you deploy a smart contract, you get this address, the smart contract address, and it's a new address each time you deploy your smart contract. So now we have the new instance here. I hope it's this one. And okay, let's try it again. So let's guess it's number 5. Oh, I rock. So it was number 5. And now let's see. Let's guess if it's number 5 again. It is still number 5. It is still number 5. Am I querying the right smart contract? Oh, yeah, no. And now the block changed. And now the number 5 suddenly is too big. So is it number 3? Too big. Number 2? Too big. Number 1? Yes, it was number 1. And then if I wait another few seconds, so every 6 seconds there's a new block. Number 1. Oh, now number 1 tells me it's too small, so it should be number 0, right? Oh, too small, sorry. So let's go to number 5. Yeah, it was number 5 again. Okay, so for all you smart kids in town in Brazil, I have another task for you. So can you maybe write a similar game so that it's not a new random number every block, but every other block, every 2 blocks, for example? How would you implement that one? Like so. But then when the block number changes, then the whole block number plus 1 also changes, right? So I'll give you a hint, like every odd number or every even number of block. How do you do it? It has to do with rounding. Okay, so since we're at the university, I will leave this assignment for your homework. Cool.
That's a good one.
Okay, so let's move on. Yeah, this is task number 1. So I hope everything is clear. If it's not, just ping me and I'll get back to you. Otherwise, I'd move on to task number 2. So currently we use this Remix, and Remix is a wonderful Ethereum tool, but it does not support encrypted transactions. So if you remembered in the Explorer, we showed this deployment transaction, But for queries, so it's the queries are read-only and they're not stored on the ledger, so we will not see it on the Explorer. But the deployment, the contract creation transaction, and also if we maybe implemented some other functions that are not queries but require transactions, those transactions would not be encrypted if you are using Remix. Why? Because Sapphire uses a so-called end-to-end encryption. So this requires certain logic on both the client and the server side. So the end-to-end encryption works in the following way. The client needs to generate a key pair. The server generates a key pair. And then when they want to send the transaction to each other, they exchange the public keys. And then what the client does is it derives a shared key from the public key of the other entity and its private key. It combines the two and it gets the so-called shared key. And this is the so-called Diffie-Hellman approach. And the same can do the server on the other side, but it's just the other way around. So it takes the client's public key and its own private key. If it combines the two, he will get the same shared key. And then how the end-to-end encryption is done? Well, you just take that shared key and encrypt your data using that key. And then when you send the transaction, the encrypted transaction, you can also send your client's public key along the way, and then the server on the other side will be able to decrypt the transaction because it has your public key and it has its own private key. The server derives the shared key, decrypts the transaction, and then executes it. Okay, so this client-side logic, which I just described, is not there for Ethereum transactions, of course, because Ethereum doesn't know end-to-end encryption. But we require it if you want to have this confidential transactions. Okay, so if you let's just quickly go to our Explorer and just randomly, watch the transactions. So if you take the Sapphire transactions, this is mainnet, and currently on the mainnet, so you only have this unencrypted transactions. Perhaps if we switch to testnet, so it's only transferring some tokens, no smart contract calls currently. Let's switch to testnet, and let's go to transactions. Yeah, right. So yeah, people are more original here. So we have this green padlock means that the transaction was encrypted, and the gray one means it's plain text, right? So it's it's a mixture of both, as I mentioned. So 99% of businesses has this transparent part of the application where you want to be public, so people can audit and verify it, and you have this private part which should be encrypted. And yeah, this is really nicely shown here. Okay, cool. So the next task we are going to do, it will not be a random number game, but it will be a safe message box, put it this way. So basically, you will be able to store a simple string on-chain, and it will only be accessible to you, right? So to the author, to the owner of the transaction which stored the message. So for this, there is already a project called Demo Starter we prepared. So this one is for TypeScript or JavaScript language. You can just go ahead and clone it. So git clone and with protocol /demo starter. If you are Python enthusiasts or Go, we also have demo starters for Python and Go. And this client logic, which does the end-to-end encryption, is also available for Python and Go, and also for Rust if you're a Rust developer. So you can just pick your favorite language for this. Okay, so I will go ahead and clone the repository. And then what we are going to do is we will build the project and deploy it using the command line. So now this is the point where you will need your local environment, Node.js that works. Okay, so I'll just go ahead and do, I think the demo starter I already have here. Okay, so I'll just use this one, but otherwise just go ahead and git clone and you will get the demo starter project. Okay, and I will go inside the backend folder and I will run the npm install. So this one will download all the dependencies. So our project, if you maybe just look at the package.json file, what are we using? So we are basically based on this Sapphire contracts precompiles, and we also use the Sapphire Hardhat package because our project is a TypeScript project, and we'll use Hardhat to deploy the project, to deploy the smart contract and to manage it and so on. And we will also use the ethers library in TypeScript. Okay, so now if I do npm build, it should be compiling the smart contract. Yeah. Okay, and just let's just peek inside the smart contract. So it's a message box. Let's ignore this CV authorization for now. We'll cover the next task. But basically, what we do is, so this set message function will store our message, and the author is the one who signed the transaction, basically. And this is it. The smart contract has these two fields. One is the message, which is private, and the other one is author, which is public. It could also be private, but it's just, for the sake of simplicity, it's public, so you can verify who stored the message, basically. Okay. So let's go ahead. So now we built the project, and now let's deploy it. So I will use this npx hardhat deploy command. And you need to provide the network. The network will be Sapphire testnet. So this is the name of the network. And I will also need to provide, the private key because the default, I think some test account does not work on the testnet. So I will just go ahead and copy my private key. So just go ahead, maybe I can show it to you. So just go ahead to your account details and then show private key. And then if you type in your password. Okay, so this is the private key of my account. Please don't drain it. And I will just go ahead and do export private key equals this. So for the rest of the terminal session, this will be like the private key, right? So now if I run again the npx hardhat deploy, it should deploy the smart contract, and it should yield me the smart contract address. All right, so we have the address. Let's go ahead and check the Explorer. Okay. So no results found on mainnet, that's expected. And on testnet, we have one result. And this is our smart contract, right? And creator, this is my account. And it's only one transaction, the one who created it, and it is not encrypted. Why? There's a special logic inside the deploy code here in our project that uses the unencrypted version of the signer So we'll get into this slightly later. But now what I'm going to do is let's try to store the message. So I already prepared. So I think I can close Remix for now. Yeah. Okay. The project already has this task. It's called set message. This task is something Hardhat brings, and it's a nice, a handler for command line parameters. So basically, you can do something like npx hardhat, and then the name of the task, it's set message. And I think you need to provide the smart contract address and the message to store hello, Puki Minas. Okay. And it seems, yes, that transaction was successfully submitted. Okay. And now if maybe I try to obtain the message to see if it works. Oh, I forgot to put the domain. Is it localhost? Let me check. Live demos are awesome. They never work as they should. So what's with the domain? Did I forget to include it? I can just put localhost here for now. Oh, sorry. Yeah, it doesn't want to work. Live demos suck. So basically here it should return the message. So I think I broke this like this morning. But basically what I wanted to say is that the flow looks like this. So maybe I should just zoom into this one. The flow looks like this. So basically, number one, the declare is a key pair. Number two, you get this ephemeral key pair from Sapphire. Why is it ephemeral? Because every epoch, the key. So this is the public key I mentioned previously, the server-side public key. This changes every hour. This is for forward secrecy. So if our keys get leaked sometime in the future, they will not be able to use those new keys with the old transactions. And the other way around, if the old keys get leaked, they will not be able to forge transactions in the future because we will use new keys to encrypt transactions with. Okay, and then the client submits the transaction. The ephemeral paratime key is used to derive the shared secret, and then the execution is performed on chain, and then the result is returned to our client and shown in the command line interface if it didn't crash. But yeah, that's the flow we are using on Sapphire to communicate and to submit confidential transactions. Right, and then there are some details here. Maybe we should touch those briefly. Basically, if you're using Hardhat, so if you're writing your app in TypeScript, and for backend part of your application, your smart contract application, we strongly suggest to use Hardhat because it's a really nice, helper to deploy your contracts, to manage your contracts, and so on. And if you just import our Oasis protocol Sapphire Hardhat package, the signer will automatically be wrapped with our Sapphire logic. And whenever you call smart contract function, any transactions and any queries will automatically be end-to-end encrypted. So it's this transparent encryption going on, and you're not even aware of it. It just is there automatically. And then if you are using some other clients, for example, if you're building a front end and you're running your app inside a browser, then we prepared a bunch of, so in the Ethereum ecosystem, there is something called WAGMI, and then there's something called Ethers, and then something called Web3.js, which is currently obsolete, and some other competing frameworks for building front-end applications. So we also, prepared for each one of those their Sapphire flavor of the library. So if you are using, for example, Ethers, you will import the Sapphire Ethers v6 package, and then you will just call this wrap Ethers signer and provide this MetaMask object, and then you will be able to again access your smart contract functions transparently, just directly, and everything will be end-to-end encrypted automatically. Okay, so this is the demo I just made. So I stored the message, and so let's see what's going on in Explorer. So if I go to our Explorer, and now here there should be another transaction, right? So we stored the message. It's the other transaction, the other where is set message? Oh, sorry, I didn't set the message. I forgot to put the network Sapphire testnet. So this is also the reason why it didn't work, yes, because by default it connects to the mainnet, and yeah. So now we should now see two transactions. Okay, and now if I want to obtain the message, yeah, so the message is hello Minas, and the author is me. So yeah, everything works. Sorry, I just forgot to provide the network Sapphire testnet parameter. And of course, on the mainnet, we don't have this contract deployed, and that's why there was the error. Okay, so in the Explorer, let's see. Now we have two transactions. The first one is the contract create, which is plain, not encrypted, and the other one has this green padlock. So the contract, the transaction is fully encrypted. You can also check the data here if it means anything to you. And let's see. I mean, even though the transaction was encrypted, we can still see some things, right? So we see how much gas it was used. We see who signed the transaction. We see where the transaction was targeted at, so our contract. You also see the size of the transaction, right? So one could assume that if you run the function that requires a bunch of parameters, that you call then that specific function, right, in that specific point in time. So this is another, thing that can leak, maybe reveal the behavior of your users or your smart contract, for example. Okay, so it's not confidential. Some things are public, so you need to keep that in mind. Like, still, the transaction, it can be seen that it exists, but it cannot be. So the call data, this part of the transaction is end-to-end encrypted, right? So the function name and the parameters are fully encrypted. And the gas is also publicly visible. So as I mentioned earlier, you have this gas padding precompile that you can use to cover this. Okay. Cool. So I think we're pretty good. So my task here is, what's the difference from the developer point of view? Like, how can you make the unencrypted or encrypted transactions inside the TypeScript code? And I can just point you here. So this message here is fully encrypted. And it basically, it just gets the contract instance and calls this message function. Set message is similarly, so it just gets the contract instance and just directly calls the set message. Okay, this is out of the box, fully encrypted. But if you look at the deploy function, you see that we instantiate a new provider here. So the provider is the object that communicates with our Web3 gateway, and that also, encrypts the transactions when it's time to do so. And here we have the unwrapped provider. This UW stands for unwrapped provider. So it won't be wrapped with this end-to-end encryption logic. So basically, we define the new provider here, and then we attach the smart contract instance here. And then if you call this deploy, everything originating from this unwrapped provider will be transparent. It will be, the transactions will not be encrypted, they will be plain. And this is exactly the behavior. This is called, or we call this smart privacy. You can have a bunch of functions that are public and that should not be encrypted to assure, provability and verifiability, so people can actually see what you are deploying and transmitting. Or you can choose that, some parts of the application should really be private, and you can use full encryption as in the message and set message case. Okay, cool. So I think we can move on to task number 3. So maybe if there are any questions so far. Okay, so the task number 3 is about confidential storage and authentication around the storage. So the smart contract state is encrypted, as I mentioned. And if you try to use this ETH get storage at primitive defined in the Ethereum white paper, you will get 0. So, I mean, you could get some random blob, but we decided that returning 0 is also sufficient for all intents and purposes. So just return 0. And the only way, if you really want your private, so if you have a member of your smart contract that you want to have access, to give access to your users, you declare it as public. So if you have, in our case, we had this author, right? Author is public. And behind, under the hood, what it does is basically the author is still fully encrypted on chain. It's still private, but the Solidity language automatically generates a getter for your field if it's defined as public. And because it's a function, it's a getter that's public, it is callable from the outside world, and because it's the getter function is a member of the message box contract, it has access to the smart contract state, and it basically just gives you, the original encrypted version of the author and decrypts it for you and gives it back to you. Right. So, what if you don't want to have, if you don't want to give everyone access to your private private variable, but you want just to have the access to some certain people, for example, to the owner of the contract, or to some, in computer science, it's called the access control list, right? You have the list of resources and entities that access the certain resources, and then you decide if you give the access or don't give the access, right? And Sapphire supports two standards here for the authorization. One is called the sign-in with Ethereum, or SIWI, and the other one is the EIP 712. And this EIP 712 is a bit tricky because it may involve signing arbitrary messages. And this is dangerous. Why? Because someone can trick you to sign a message that contains the transaction that could drain your funds, for example. So the user could just see, you know, some binary blob in his MetaMask. The website wants to just sign this message, you know, I won't do anything. It's just a query, you know. Queries are, as I mentioned, a query cannot change the blockchain. But if the query contains the transaction that could change the blockchain, and if you sign that transaction with your key, then the attacker could just take your signature and generate the same transaction of the message you just signed, combine the two, and submit the transaction and drain your funds, right? So you should not just blindly sign stuff, like as we've seen in the Bybit hack by the Koreans and so on. So never do blind signing. That's really, really bad. So yeah, my point was that EIP 712 is slowly moving away from the front-end applications. So if you're running your backend app and you are the owner of your code, then still you can use the EIP 712. But from the front-end apps, because you visit each website has a different code and you don't trust the website, you know, under the hood, the EIP 4361 standard is more strict, and the messages are more strict, should be used for signing the queries. Or you can just have some, you know, arbitrary custom logic, like just let's make a magic word like open sesame, and then you get your private member as you return the private member. So you hard code basically the secret key somewhere or something like that. Yeah. So that doesn't require any fancy EIPs, ERCs. You just build your own authentication logic. Okay. And there's another term I'd like to talk about. It's called impersonation. So in Ethereum, you can call queries, and you can also arbitrarily set who is calling this query. In other words, this message.sender, which we used, for example, to store the author of the message originally, this message.sender can be set to whichever value you want in Ethereum, because it's very common in Ethereum to simulate a transaction in form of a query, and then see like what would happen if this transaction would be executed on chain, which fields would be changed, what would be the return value. And also, of course, you must be able to set arbitrary this message.sender field, you know, to simulate what will happen if someone else sends a transaction, for example. And of course, this is absolutely fine. There are no issue with this because the blockchain is transparent. The contract state in Ethereum are public to anyone. So, I mean, you cannot do any harm if you just, you know, simulate transactions, because you don't basically reveal anything. But when it comes to Sapphire, we hide the contract state. And if your business logic is around the message.sender, which is the most natural way to build smart contracts, so basically you check whether a message sender is the one who is allowed or not allowed to access your private members, then you have a problem. And for this reason, we prohibit setting the message sender. In other words, if the query is just unsigned, then the message sender will always be 0. So this is the original message sender in your entry point of your smart contract. Otherwise, the message sender, you know, is always the function caller of your function. But the first the first entry point function of your smart contract, that message sender will be 0 if the view call, if the query was not signed. And if it was signed, so I'm talking about the EAP 712 in this case, then the message.sender is not arbitrary. It is set exactly to the one who signed the query. Okay, so by doing so, you can then again build your authentication logic around this message.sender field, and you can rest assured that no unauthorized access will try to peek into your smart contract and simulate some queries and maybe leak some information, right? But keep in mind, so you really need to check this message.sender at the very beginning of your function. If you forget it and maybe you check it somewhere in the middle of the function, you may already reveal some information, again, regarding the balance, if it's greater or lesser, because then attacker can already, try to adapt guess and maybe some other parameters and try to leak data. Okay, so now if you check our smart contract, we briefly went through before this set message function, but how it's done in practice, we added an interface called CV auth inside our library. And basically, if your smart contract extends this CV auth, it gets this auth message sender helper for free. And the is the following. So you sign the query using your MetaMask, for example. And this query is basically the sign-in message. So the website is inside this message, who is the caller of this query, what is the address of the smart contract, and so on. And if you decide to log in, then you will get this authorization token back. And then you can use this authorization token for whichever function you want to call inside your smart contract. And this auth message sender helper will take this authorization token and it will extract the message sender, which is then used to authenticate your logic. So in our case, we basically log in and then we get this auth token, we provide this auth token, and then the auth message sender will return our address because we are the one who signed this query, and this logic here will succeed. Okay, so without further ado, maybe let's just go ahead and try this in practice. So I already tried it in the CLI. So CLI in our case also does this CV magic under the hood. So maybe I can just skip to the front end. This is more fun part. So our contract, what is the address of our contract? It's this one. So I'll just go to our front end and I will add the smart contract address to the .env file. Okay. And yeah, the Sapphire testnet network is this one. We will be running the Sapphire testnet. Okay. And if I just now do pnpm dev, I think I can go ahead and connect. Okay, so this is the front end for our app. A very simple one, but it serves the purpose. And now if I want to reveal the message, okay, I have this sign in with Ethereum. And it's really nice because this CV standard also checks whether the URL, the local host in our case, matches the one that's expected on the blockchain. Because you can have some malicious websites, try to forge the sign-in requests, but if they don't live on the specific URL you provide during the smart contract deployment phase, then this sign-in request will put a big red exclamation mark here and say warning, like you're visiting the wrong site, you should not sign this message, and so on. So it's not bulletproof. Users are really original when it comes to this, but okay. So now if we sign this message, we receive the authorization token, and with the authorization token, if you look at the logic of our smart contract, so the getter here requires where's the it requires this isAuthor modifier, and this isAuthor modifier takes the authorization token, decodes it here, and because we matched the original author, we are allowed to retrieve it. If I change the account, for example, if I change to someone else, I know this one, connect. Okay, let's reload. If I try to reveal it now, okay, let's sign in. Yeah, I will not get the message. And in fact, if I check here, I should receive some revert error here, or yeah, maybe I hide it. Okay, so this is the authentication we do. So the bottom line is we have this confidential smart contract state, and you should really protect it. You know, it should not be. You should be careful when you build your smart contract. You need to implement this authentication inside your smart contract to really, you know, reveal any sensitive data to whoever is allowed to use it. All right, so I think this concludes our task number 3. So yeah, this is a nice screenshot. Okay, so this is the practical part. So in the next few minutes, I will just briefly go through the cool stuff you can also do on Sapphire, trying to motivate you to build on Oasis. Maybe I'll just pause here for a moment, and if there are any concrete questions with the task we had. So if you go to our GitHub Oasis protocol, and if you search for demo starter, you have three demo starters here. So the original one is the TypeScript one, but we also have the Python flavor, which is basically the same contract. So again, we store the message, we retrieve the message. But if you look at the Python logic here, it's slightly different. You know, so we are using this Web3. Where is it? Here, yeah. So we're using this Web3 library, and we are using this Sapphire Pi package. So if you go to PyPy, we are maintaining this Sapphire Pi. This one. So this is, for example, the Python. And this is also really cool because people are now using Python, very common to write their own AI agents, for example. And yeah, this is more and more getting useful for storing secrets, for example, you know, passwords, or maybe some tokens even on the blockchain, and then retrieving it inside your AI agent, for example. And then if you are a Go enthusiast, we also have the demo starter for Go. And we also support Rust, but we're not, yeah, we didn't build the demo starter for Rust yet, maybe in the future. Yeah, so the tricky part here is what will you do with the end-to-end encryption? Yeah, because you can use basically any Ethereum tooling out there to build your smart contracts, but there are some Sapphire specifics. For example, end-to-end encryption is one of those. You will not get if you don't, implement it yourself. This is why we offer so-called wrappers. The TypeScript wrapper, the Python wrapper, the Go wrapper, that basically they wrap your transaction and make it end-to-end encrypted. Okay, so maybe let's try to brainstorm a bit. So what to do next? The first thing you will notice when you deploy, when you start building your dApp, is that, well, while you're building it, you need to test it. And using testnet is sometimes, awkward, or maybe not applicable, or that you don't have the internet access. So in this case, you want to run localnet. And basically, the localnet Docker image we prepared is really similar to maybe if anyone used the git --dev command. It basically funds 5 accounts. Each one, I think, is 10,000 tokens. It's running inside your computer. Doesn't require any internet access. It also doesn't require any Intel SGX, TDX hardware. You can run it on your Mac, for example, or Raspberry Pi if you want. So it will spin up basically the Oasis core node. It will spin up Sapphire running in that node. It will also spin up the Explorer, the local instance of the Explorer, so you can browse, I think it's port 8548, which you can connect to locally, and you have this wonderful Explorer running locally to explore the transactions and blocks. So why is this useful? So for localnet development, and also for the continuous integrations, right? So if your dApp lives on GitHub, you want to have this CI thing that tests your PRs, and in that case, you don't want to, send your smart contracts deployed to testnet each time. You want it to run inside the, the CI instance of your GitHub Actions machine. So yeah, this is really, really useful. I think we even devoted one chapter in our documentation. So it's localnet. Yeah, here it is. And you can run it. So you can run it inside Docker like so. And I think there's also a snippet for running it, inside GitHub Actions. So if you use something like this, the localhost 8545 port will be accessible, and you can just point your RPC parameter to that URL, and you will connect to the localnet, and you can then deploy your dApp too. Okay. The second thing is, so I already briefly talked about shared secrets. So when it comes to end-to-end encryption, this Diffie-Hellman, elliptic curve Diffie-Hellman more specifically, is really, really useful. What I didn't tell you is that you can also do shared secrets in Solidity on-chain. So we are specific subcalls, maybe, I think I don't have it here, but the derivation function that you can get the shared secret from the keeper is a primitive inside the Oasis Sapphire, and once you get the shared secret, then you can do wonderful things like the encryption and decryption of messages, everything on-chain, everything in Solidity. So this is something you cannot do in Ethereum. You can do on Sapphire it really, really nicely. And as a proof of concept, we built a simple quiz on our chain. And the idea here is that if we have a live event and we hand out coupons, and that coupon is basically encrypted message. And when you enter your coupon, when you visit the quiz website, enter your coupon, that coupon is decrypted on chain, and there are some information inside that message, like the username or some sensitive data. And this is so an example of the application you cannot do on other chains, for example. And here it's really a straightforward approach. So on-chain encryption and decryption is also used for emitting encrypted events. So when you emit the event inside the smart contract, that event is publicly visible, and it's the same in Sapphire. The content, the event ID, and the content is public. If you want to encrypt it to make it hidden, you need to use this on-chain encryption primitive. Okay, and another feature you can do when you have this on-chain encryption available, you can do something like logging in to your services. So the way, for example, if you know WebAuth, for example, or passkeys, basically you can just store a footprint or an ID of your user on-chain, and then each time the user has their own hardware device to authenticate, you can check whether the user is really the one who claims to be everything on-chain. So basically you can write a getter in your smart contract, and you do the authentication logic based on the hardware device the user had. For example, the fingerprint on their Android phone can unlock some private field of your smart contract. Okay, so this is a really powerful tool. You can then build your apps around it. If you then imagine you can connect a DEX, so on-chain exchange, you can directly pair with your fingerprint on your Android phone, for example, to trade something or to authenticate. So no more usernames, passwords. So everything is seamlessly integrated and just works. Okay, the next powerful feature is the autonomous contracts. So what's it about? Basically, if you can store a private key on chain, that private key can be used to sign transactions. And by doing so, you can basically fix the holy grail of Ethereum, again, one of those holy grails. Like, how can you send transactions without paying for the gas? Why? Well, because users may not have their wallets, may not have sufficient amount of tokens to pay for the gas, or may not be Web3 natives. They just want to, for example, go to the elections and submit their vote, and they have this proof, they have their ID card that they are eligible to vote, but they don't have the private wallet to pay for the gas fee to submit the transaction on chain. And since we have this confidential contract state and on-chain encryption primitives, you can basically get the vote from the user, and then you can sign that vote with the private key that has some gas on chain, and then you just return the signed transaction back to the user. The user can verify whether the transaction is still legit, that you didn't maybe change the vote, and then the user just sends that transaction because the gas is being already paid for. And not just that, by paying the gas, you also conceal who submitted the transaction. You hide the actual user who submitted the vote. You get the anonymity. Okay. So this is called the autonomous contract. So the contracts that can sign the transactions on their own behalf. Yeah. There was a huge debate maybe 2 years ago in the Ethereum community about the account abstraction primitives. So here you don't need any account abstraction. You just store the key directly on chain and then use it to sign the transaction, and that's it. So really straightforward. We also built a proof of concept. If you go to voteoasis.io, you can just create a new poll, for example, and you can decide whether the poll is gasless or people need to pay for the gas fee. And you add the options, add questions, and just share the link, and people can then vote. if they are not crypto natives, they can just use gasless option and they can and yeah. Okay, another technology we were building is a set of libraries for cross-chain dApp development. So suppose you already have your dApp running on Ethereum, Polygon, whichever chain you want, and you just want to have a small chunk of your application which requires confidentiality to be executed on Sapphire, right? And in this case, you need to have this cross-chain bridge, some primitives of that, either running the actual bridge and monitoring the transactions, or just relaying the Merkle proof that the transaction was really submitted on the other chain, and then that proof can be verified also on-chain, not just on some third-party app. So this is called Oasis Privacy Layer, or OPL. What else? Okay, so the most hot topic for this year, so Sapphire is so 2024. In 2025, what we're doing is the runtime off-chain logic, or ROFL. So what we're doing here is that suppose you have applications like gaming or AI inference, or even maybe AI training, chat apps, even maybe simple websites. So can you generalize on-chain applications to make it more responsive, cheaper to use, more autonomous in terms of that the logic runs all the time and not just when you send a transaction? For example, when we wanted to generate a new random number, we needed to have this transaction all the time to change the contract state. Wouldn't it be nice if the smart contract could just, you know, live on chain and do something on their own every block or so? So how can we do it? So how can we combine the off-chain and on-chain world? So we came up with this. We came up with this concept that people, if they have the TDX hardware, so the TDX is the next generation SGX. If they have TDX hardware, then they can run their Docker. They can write their application. They can pack it inside the Docker container. They can even use Docker Compose to integrate multiple containers inside into the application bundle, and then they can wrap this Docker application inside ROFL application. So the step here is that once you have this ROFL application, you can deploy it on chain, and then you can, if you have your own ROFL node, your own hardware, then you can run it yourself, or you can run it on whichever ROFL node for the provider there is offering the nodes for a small fee. For example, you pay 100 rows, and it gives you an instance for 1 day, for example, and then you can basically run your Docker inside his TDX trusted environment. So this ROFL app is like a very strong concept when you have a fully distributed network of nodes offering compute. And then on the developer side, you have people writing their applications, and then they can basically deploy the Docker app, their Docker app on whichever ROFL node they want, and the billing is done on-chain. The ROFL management of their application is done on-chain, so there is no censorship, no KYCing. Most cloud operators now require some form of KYC, for example. It's awful, but yeah, so this is the whole new network, whole new concept we're trying to build here, to allow compute for everyone. So if you're interested into this concept, we are also having this ROFL 101 workshops. You can just go ahead to docs.oasis.io/build/ROFL, and yeah, there are some quick starts there. For example, how to build a Telegram bot running inside ROFL. So it's really strong concept, and it's also seamlessly integrated with Sapphire. So you can store secrets on Sapphire, for example, and access it directly as environment variables inside Docker container Ruffle application. Okay. What else? Okay, and I also invite you to run your own Oasis node. You can become a validator and earn some fees. If you have a TEE hardware, so SGX or TDX, you can also run a Sapphire paradigm node to earn some extra fees. So whoever pays the transaction fee, you will get it if you verify the block. You can also run your Ruffle node and earn some fees. Or if you just want to hack and you don't want to rely on the public infrastructure on the Web3 gateway, for example, the Oasis Foundation is maintaining, you can just spin up your own client node and your own Web3 gateway node, and you can then maybe explore the network, do some queries on what the blocks look like, what the transaction looks like, because our public Web3 gateway is throttled, so there is certain amount of transactions and queries you can do, and then you will be throttled, and you will need to wait for a few moments to continue. So this is everything is documented here if you want to start running your node. And yes, finally we have a playground. So the playground is a website that collects all fun applications during the hackathons, or even the proof of concept our team built. So if you look, for a quiz, there's this confidential quiz I was talking about. You can also filter. So if you want to learn, for example, give me all the Python projects, or if you want all Ruffle applications, is this ones. So yeah, it's pretty. If you want to explore and just look around, like what exists currently on the Oasis network, you can go ahead and browse through this. Okay, and finally, so I'd like to thank Professor Lilo Ivero and your institute for exact sciences and informatics and the Catholic University of Minas, to host me. And this wouldn't be possible if it wasn't the Oasis University program we're having. So for students, students can have internships with Oasis, even scholarships. Maybe they can attend hackathons or join the ambassador program. If they build any other projects during the course, the courses, maybe they can use Oasis for the project, and we will spotlight it. And they can also earn some swag, T-shirts, power banks, even. Professors can have us as guest lecturers. We have some research grants. Also, if any of the professors want any course materials, they can just ping us and we'll give them slides or maybe any images or diagrams they want. We are also sponsoring industry conferences. There are a bunch of those. So we just had ETH in Amsterdam. There will be ETH Belgrade in the upcoming days. Then there's the ETH CC in France this year. We have on the other side the ETH Denver. So really strong Ethereum conferences where Oasis is also present, and we can sponsor attendance if you are for any partnerships, for example. All right, and yes, we welcome you to form the community, the new Oasis community at your university. So we have these incentives for Oasis ambassadors. You can check out. And I think, yes, I'm way over time, but this is it from my side. If there are any questions, answers, maybe proposals for improvements, feel free to ask me. Thanks.
Hey, Matej, I would like to thank you a lot for your availability. You were really didactic. I'm not a technical person. I don't know how to code, but I did learn a lot. I was surprised with how much I learned, and I don't even code. So thank you. I hope the students here today realize the privilege that they had with you sharing your knowledge with them. It's an opportunity for them to step into this industry that it is still a recent industry. We began in 2008, 2009 with Bitcoin, and we're still developing a lot. It's an industry that is ever growing. It was the industry of the future, but it's now the industry of the present. So I thank you a lot. I hope the students realize the opportunity that they have here. And that's it. Thank you. It was great.
Okay, I would be glad to make another workshop, and looking forward for any future cooperations. Sure.
Yes, and that is something I would like to stress. I don't know if it was clear, but this is for you students. If you want to develop something on the Sapphire blockchain, on the Oasis ecosystem, Oasis has a program of grants, which would be financiamentos, to help you build something on the network. They can spotlight it. This is your opportunity to get into this industry. So I wouldn't miss it if I were you. And that's it. Yeah, I'm always available. Yeah, you can reach out to me. Anyone who's interested in developing something, Ilu, you can pass on my contact to them, to the students. I'm free for anything. Let's see. Yeah, I don't think so. People are quiet today.